Hello, good evening, everyone.
Hello.
Uh, this is the welcome to the online interactive lecture series being organized by the India-based Neutrino Observatory INO project. As many of you know, who are probably attending most of these talks, we already had several talks. In fact, last 5 weeks or so. So, welcome to sixth week of these series of talks. This week we have today, starting with Dr. Lakshmi Mohan, talking on GeV neutrino oscillation experiments, and we are going to have another one on Wednesday on how will the INO detector is going to record neutrino interactions, and followed by another talk on Friday by Professor Kadari Majumdar on a CMS talk on the first decade of LHC over and two more to go. So this is going to be the physics coming out of LHC. So that is the program for this week. Of course, we have equally exciting lectures coming up even a week later. Okay, so with that, let us come to today's talk. As I said, this is going to be delivered by Dr. Lakshmi Mohan. Uh, in fact, Lakshmi Mohan is our own, you can say, INO product. She belonged to the second batch of the INO graduate training program, our own PhD program. Uh, so this is actually in 2009. She joined this program in 2009, and instantly you might remember another speaker who featured on this series of talk, Dr. Munmun Devi. She was also incidentally from the same batch, that is the second batch of GTP program. And she did her work under Professor D. Hindumati from IMSC Chennai. Uh, Lakshmi actually did her MSc from School of Pure and Applied Physics, Mahatma Gandhi University, Kottayam in Kerala. And of course, as I said, then she joined the INO program where she worked with Professor Indumati. Subsequent to that, she did postdoctoral fellowships, one at PRL with Professor Subhapati Goswami, who also gave a talk on this series, followed by another one in IIT Madras with Professor James Libby. And now she's at NCBJ. NCBJ stands for National Center for Nuclear Research uh, at in Poland, Warsaw, and she's working under with Professor. I'm not sure if I can pronounce the name properly. Jusna Laboda also works with the T2K experiment. Some of you would still remember the talk on the T2K by Urjit, and this there has been an excitement on results from the T2K recently. And Lakshmi's main field of interest is neutrino oscillation physics and also the detector simulations. So these are the few words on Dr. Lakshmi Mohan. With this, I invite her to start her lecture today.
Thank you, sir, for the nice introduction. So I'll start my talk. So I hope that it's visible. The PPT is visible, no?
Yes, yes.
Okay. So good evening, everybody. So I will be talking about some GeV neutrino oscillation experiments, and the disclaimer is that I will not talk about anything beyond standard oscillations, as in no sterile neutrino, no decay, nothing. I'll be talking about standard oscillation with GeV neutrinos. So this is our mandatory picture for standard model of elementary particles, and by now many of you would be familiar with these three neutrinos, which whose oscillations we are studying. We are interested in studying. So this is the source of neutrinos based on our energy. Energy. This is the classification based on energy, and these are the different sources of neutrinos. So in the previous many talks, we have heard about a lot of about Big Bang neutrinos, then geoneutrinos, reactor neutrinos, solar neutrinos, supernovae, extragalactic, and also we have atmospheric and accelerator neutrinos. So atmospheric neutrinos and accelerator neutrinos are of similar energies. So here, if you look at this, so this is from zero point 0.1 MeV, sorry, it's actually zero point 0.1 GeV, about zero point 0.1 GeV to about 100 or thousands of GeV, and accelerator neutrinos are of the energies of a few GeV. So what is the difference between, is there any difference between these two neutrinos? Because their energies are similar. So are they very different from each other, or are they similar? So both these come from the decay of pions and kaons. One is produced in atmosphere and the other is produced in lab. So this I'll show in a minute. So these are the two oscillation, sources of neutrinos which we are interested in. And why are we going to study GeV neutrinos? Because this is the three flavor or mixing matrix. So this is the 3x3 mixing matrix in vacuum. If you remember, so if you had attended Uma Shankar sir's talk, you would have remembered, and many other talks, Shubhavati ma'am's talk also. Uh, there are we can decompose. Write this matrix as a product of 2 3 1 3 and 1 2. So that means there is a 2 3 sector which is given by atmospheric or accelerator neutrino experiments. There is the 1 2 sector which is the solar neutrino experiments, and 1 3 sector which is probed by reactor antineutrinos. So this thing which is marked in red is the theta 1 3 and delta Cp. So the other theta ij are in general. So this one Cij, Sij mean cos theta ij and sin theta ij, and these are the mixing angles. And this is the delta Cp, that is the electronic Cp violation phase, whose value we do not know exactly, but there is this slight hint towards it. And we want to measure this. So what are the things we do not know? So GeV neutrinos are usually used to study 2-3 oscillation parameters. And this also, that is the theta 2-3 mixing angle. Then in addition to that, we can study neutrino mass hierarchy, the unknown mass hierarchy. So, and the delta Cp phase. So this is the current status of neutrino oscillation experiments. Here, this theta 1 to delta m squared are known. So if you look at this picture, so this shows the question of mass hierarchy. So this is m1 squared, m2 squared, m3 squared, that is new masses of nu1, nu2, nu3. So we do not know if the mass of nu3 is greater than m1 and nu1 and nu, that of nu1 and nu2, or if it is less than the other two. We know the hierarchy of this and the magnitude of this delta m squared from solar neutrino experiments, that is 7.6 into 10 raised to minus 5 eV squared. And the atmospheric mass square difference, we know the magnitude of it from these experiments, which some of the GeV neutrino experiments, and but the sign of this quantity is not known. So this is a long-standing problem in neutrino oscillation physics. And we do not know exactly precisely what is the octet of theta 2 3. So globally, we can some for number is around 48.6 approximately. And there is a mild hint towards maximal Cp violation from different experiments, and the T2K result also was there. So then this angle theta 1 3. So theta 1 3, please remember, this came from the reactor anti-neutrino experiment. So Double Shoe, Diabe, and Reno measured this angle, and the measurement of this angle was actually very, very important for our studies. Why is it so important? So before I go into that, let us just recap how will we detect a neutrino. So we all have heard over the weeks that neutrinos are chargeless particles. So neutrinos cannot produce direct signals or direct tracks in the detector. So the detection is always indirect. So what we look for is the charge current or neutral current in the target material. So the neutrinos will come and interact. If it's a charge current interaction, it will produce charge level particles. If it's a charge level interaction, it will produce final state plus some hadrons. And if it's a neutral current interaction, it will produce hadrons in the final state, and the other neutrino will just escape. So we cannot detect. So all these neutrino experiments are very huge detectors. Why are neutrino experiments so huge? So that is again attributed to the weak interaction of neutrinos. So if we take the suppose we are there is no oscillation, we are just trying to find out how many unoscillated events we can detect in a detector. So this unoscillated number of events is given by flux times cross section times number of target materials available for neutrino interaction times exposure of the detector. So what is flux? So flux is the number of neutrinos, how many neutrinos are available, and then cross section. So cross section is something natural property of neutrinos. So when we build a neutrino, we cannot do anything about a neutrino cross section because it's natural, so we cannot change it. But the other three things we are in our hands. So so we can run our experiment for as long as we want. Say for example, if we take super Kamiokande experiment, it has been running for almost 25 years now. So as long as we want, we can run it, or we can make the detector as big as possible. For example, or give more nucleons or more target material for the neutrino to interact with. So we can make a kilometer cube ice cube, or we can make a smaller detector, but denser detector, say with iron, like ICAN. But the energies are different there. It depends on the energy physics we also want to study. And the flux of neutrino. So flux of neutrino is like how many neutrinos are coming from your source. So that in atmospheric, so in GeV neutrino experiments, we consider two sources. One is the atmospheric neutrino experiments, and one is the accelerator neutrino experiments. So atmospheric neutrinos are produced naturally, so we cannot control the flux. So in atmospheric neutrino, these two things we cannot control, but the other two things are in our control. But in accelerator experiments, we can make a highly intense beam also. So and then study the physics we want to do. So in presence of oscillations, this number of events will be modified as a product. So if oscillation happens, this will be again, that number of events will be reduced. That's what people were seeing in atmospheric neutrino experiments, right? If you remember, when Super K observed the oscillation first, there was a deficit in the mu-like events coming from the other side of the earth, which meant that they were oscillating. So this oscillation can be in vacuum. If matter is present, that will be modified by matter. So now let us look at how this one example. I'm showing the T2K and SK detector here, atmospheric neutrinos versus accelerator neutrinos. So in atmospheric neutrino experiments, like I said, both are coming from, so these two experiments have neutrinos coming from the decay of charged pions. Or kaons, charged pions and kaons. Pions are mostly dominant. So let us look at atmospheric neutrinos. So we know that in the upper atmosphere, primary cosmic rays will interact with the molecules there, and then they will produce pi plus and pi minus. This pi plus and pi minus during flight will decay into mu plus and mu minus and a neutrino, nu mu and nu mu bar, and then this mu will further decay into an electron, and then so if it's a mu plus, it will decay to E plus and nu mu bar, and if it's a mu minus, it will decay into E minus and nu mu. And again, because there is this kind of decay is there, so there is a nu E also. So we get from atmospheric neutrinos, for every nu E neutrino, there are two nu mu's. So if we take the total flux of atmosphere, ratio of the flux of nu plus nu mu bar flux divided by nu mu plus nu e bar flux, then we will get approximately 2 in the energy range which we are interested in. So this is so all these will come there, and also the muon is also there, right? So this muon, so this is always depicted, this is supposedly earth or a mountain, or if we go underground, we can filter out this muon, and this muon, so this neutrinos will pass into the detector. But if it is coming from upside, we will not see oscillations, but Earth has atmosphere all around it, right? Earth is a round object, and so it has atmosphere all around it. So if we have a detector somewhere on one side, all the neutrinos produced from below or coming from below and passing through the earth, that long distances will oscillate, and we will get an oscillated signal in the detector. So this is the super K detector, which actually discovered atmospheric neutrino oscillations. So super K detector is also the far detector for this T2K experiment, which is a long baseline experiment. So this long baseline, so the L by E is determined by what delta M squared we want to probe. So we want to probe the atmospheric delta M squared, that is of the. Hello. 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 Somebody's mic.
I'll take care. You go ahead.
Okay.
I'll
Okay.
mute. Yeah.
So what
Lakshmi,
happens
go ahead.
is so so we want to probe the delta M squared 32. So that delta M squared 32. So depending on that delta M squared 32, we can calculate what L and E we require, or what Ly range we require for our experiments. So T2K is also now. In accelerator neutrino experiments, the first step is always the same. So the first step will be we impinge a high energy proton beam on a target material. So either a graphite target or some target material, and that from there we produce pi plus and pi minus. Then this pi plus, now in accelerator beams, in atmospheric neutrino experiments, both neutrino and antineutrino come together. We cannot put a magnetic horn in the atmosphere, upper atmosphere, and selectively, I mean, all around Earth, we cannot do that. So we have all kinds of two flavors of neutrinos plus neutrino and antineutrino. But in accelerator neutrinos, we want to select particularly nu mu or nu mu bar. So what will allow this decay to happen in the region, in the decay pipe. So we'll just put a magnetic horn, and before this decay can happen, we'll plus and pi minus will be selectively taken depending on what beam we want. If we want a new allow pi plus to decay, and select pi plus, and nu mu bar will select pi minus with the help of a magnetic horn. So there is a decay volume, and it will create, and this decay will happen. So once this decay will happen, all the muons coming from this will be there will be a muon monitor, and there will be a beam dump also. That muon will be absorbed. So there is only this first step happening. The second step we are not allowing to happen, because we want to have a clean nu mu or nu mu bar beam, because we are always looking at the disappearance of nu mu or the appearance of nu e from nu mu beam. So or nu tau from that beam, depending on the energy. So conventional, so this is the conventional accelerator neutrino experiment, which allow this to decay in flight. So here is the actual beam direction, so the pi plus direction. So when you have that kind of decay, when all these pi pluses are decaying, then you will get a broad energy neutrino energy spectrum. But because this is a broad energy spectrum, many other background effects can come in. So we want to cut out all those background tail events. So what do? We put the far detector, or align the detector in such a way that the beam in such a way that the far detector is at an angle, some angle with respect to the actual beam direction. So for T2K detector, this off axis, this is called the off axis technique, and this off axis is about 2.5 degree. So in another experiment called NOVA, so NOVA is another off axis experiment, and that is 14 milliradian off axis. So the thing is, so depending on the angle, we will select, we can make this peak to coincide with the oscillation maxima. So this oscillation maximum for 295 kilometer, so happens around 0.6 GeV, and here the oscillation, this flux peaks at 0.6 GeV. So we know that, okay, maximum number of events are coming from this energy range, and this is our. So there will be some intrinsic beam background for every nu mu beam or nu mu bar beam, but that beam background is very small. Suppose mostly nu mu purity in a beam will be say 97 or 98, 99% kind of thing. And there will be a minor this thing, but that is understood. So in most of these detectors, accelerated neutrino experiments also have a near detector. So what is this? So in atmospheric neutrino experiments, we do not have a near detector at all. Or most of the, I mean, at all, because the what does near mean? So this near detector is at some smaller distance from the beam. So this before oscillation, the beam will pass through the near detector, or we can collect some unoscillated events in the near detector. And why is it needed? We want to know that the beam composition, we want to know that it's actually a UMU beam, or whether it's a UMU beam or a UMU bar beam, or does it have any contamination and so on. We want to measure the flux of this beam. So we are supposing that, okay, we designed our experiment in this particular way to produce these many things. Are we getting that many expected number of events? So then we can say that, okay, this many started, and the far detector, after oscillation, we got a reduction in the number of the events. So we need that to measure the fluxes and also the neutrino cross section. Many of these experiments, near detectors measure the neutrino cross section on different target materials also. And this for T2K, there is the off-axis near detector is ND280, and this muon, there is another detector called INGRID, which beams the beam profile and intensity. And of course, our far detector is the favorite Super K detector, and it can measure both atmospheric neutrinos and accelerated neutrinos. But atmospheric neutrinos, if you look at this, so this is a cylinder of diameter 39 centimeter and approximately height also 39, sorry, not centimeter, meter, and 39 meter and 39 meter. And atmospheric neutrinos can come from any direction. So the entire detector, so this is the top and bottom, and this is the barrel portion of the detector. So this entire detector is covered with, so there is an inner part of the detector and an outer part of the detector, optically separated by photomultipliers. So this there are 11,000, approximately 11,000 140 something PMTs on the inner side and about 2,000 on the outer side. And this inner detector will, so, and the water is the detector material, and atmospheric neutrinos can come from any direction. So this PMTs, any side, all side PMT will give the direction, and from there that we can determine the energy also, that I'll tell later. But for beam, there is always one direction. So it's always coming from one direction, and we know what direction it is coming from. So we can keep on accumulating data. It is called forward Horn current and reverse Horn current data in accelerated neutrino experiments. So, so we either take nu mu data separately or nu mu bar data separately. So that is the difference. So here in accelerated neutrino experiments, we have a control over our the flux of neutrinos, and here we do not have a control over our flux of neutrinos. But one very important difference is that atmospheric neutrinos have a wide range of energy, that is 0.5 to not zero point 0.1 to say hundreds of GeV, and the L available is like 15 kilometer to about the diameter of Earth, which is like 12,000 kilometer. So the L by E range in atmospheric neutrinos is huge. So for many cases, many things can, severe constraints can be put on several things by atmospheric neutrinos. But at the same time, accelerated neutrinos, one accelerated neutrino have one small energy range and one L. So that L by E range is different. But here we have pure nu mu or nu mu bar beam. So the physics also differ accordingly. So accelerated neutrinos, you are okay, go to the other slide. So this is these are the two major differences between accelerated neutrinos. Otherwise, if you look at accelerated neutrinos and the neutrino energies are the similar. So and only fluxes are different. So and so let us look at three flavors. So why are we taking all this pain to looking at neutrinos from several different sources? I mean, can't we just do with one experiment? Why do we want so many different experiments? So the so many different experiments can give us hint about several different things. So we need all those things. So this is our three flavor mixing matrix in vacuum. I'm just showing, and this is our oscillation probability. So it has a real part and an imaginary part. So for neutrinos, this is the real part, and plus, and antineutrinos is minus. So, and this imaginary part contains the CP violating, leptonic CP violating term. So, and if we can take the difference between these two probabilities, we'll get the CP violating term. So why is the CP violating term very important? Because that is, if you remember Urjit sir's talk, that CP violating phase is very important to our knowledge about the matter-antimatter asymmetry of the universe. So now let us come to non-zero theta 1,3. So I mentioned that the determination of non-zero theta 1,3 was a very crucial input to the or both atmospheric and accelerator neutrino experiments. So earlier when the accelerator, the first generation accelerator neutrino experiments were called disappearance experiments. And usually if you're looking at nu mu going to nu mu, we usually call that disappearance experiments. So experiments like K2K and MINOS were like we're looking at mainly at nu mu experiment, nu mu disappearance. Why was it called so? So nu mu can go to so the in 2-3 people were saying that nu mu is going to nu tau. That's why this oscillation was happening, and this atmospheric neutron oscillations were happening. So what happened? So but we cannot detect nu tau that easily. For nu tau product to detect nu tau, we have to have a very high energy experiment, and many of those LBL long baseline experiments were not energetic enough. So we were all looking at the disappearance probability. So MINOS and K2K looked at the disappearance probability. But if we have to have appearance, so the next thing is that if the oscillation, if there is three flavor oscillation actually, then we should be able to see appearance. That is nu mu oscillating to something else. That something else is the nu e. For these kinds of energy. So why is that important? If we had, before the theta 1,3 era, many of the experiments had a goal of identifying, nu appearance. So if we had detected nu e, if we detect nu e in our detector, that meant that actually nu to nu e oscillation is happening. That also means that theta 1,3 is non-zero. That is one indication that theta 1,3 is non-zero from this accelerator neutrino experiments. That is, this before all the other three experiments actually showed that theta 1,3 is actually non-zero. So this it indicates a non-zero theta 1,3, and then this is so the for accelerator experiments, we have two goals. One is this appearance will indicate non-zero theta 1,3. Then if theta 1,3 is non-zero, then we will be able to able to measure the leptonic delta Cp phase. So had theta 1,3 being non-zero, we would not have been able to make this measurement, but theta 1,3 non-zero theta 1,3 made everyone happy, because now we can measure delta Cp also. So in the three neutrino paradigm, so Cp violation can occur only if all the three mixing angles, that theta 1,2, theta 1,3 and theta 2,3 are non-zero. Earlier people had, theta 1,2 was very precisely known from solar experiments. Theta 2,3 approximately was known to be around 45 degree, and from those other disappearance experiments, and then theta 1,3, that confirmation came from the reactor anti-neutrino experiments. So now this is for delta Cp. What about hierarchy, neutrino mass hierarchy? So these are the two outstanding problems in neutrino oscillation physics now. So hierarchy, if we plot the oscillation probabilities in vacuum, both neutrino probability and anti-neutrino probability will look similar. So how do we do this? Luckily for us, we have matter. And luckily again for us, theta 1,3 is also non-zero, which means that there will we can probe matter resonances. So matter resonances can happen only if theta 1,3 is non-zero. So theta 1,3 has an implication for both delta Cp and hierarchy. So now if resonances happen, for a given hierarchy, neutrinos will behave in one way and antineutrinos will behave in another way. So if we observe the oscillation probabilities or event spectra of neutrinos passing through, which have come by after traveling so much distance in matter, then we can separate between what is the hierarchy. So I'll show this. So this is called earth matter effect. So again, for GeV neutrinos, we are interested in earth matter effects. So because of that L by E thing. So then for us, this is our earth. So if we put a detector somewhere here, say usually it is 1 kilometer underground, because we want to observe cosmic rays. So if we put a detector somewhere here, so we have L coming from all different directions. So all these cells. So it can come from, this is the outgoing neutrino and these are outgoing neutrinos, the core of the earth also. So
Lakshmi, your voice is a little bit cracking.
so many different layers are there. So hello, can you hear me, sir? Till when did you hear?
Just about 10 seconds, 20 seconds ago.
This core crossing due to this.
Now it is better.
I think it's the headset. So one second.
Okay.
Probably this headset is
now
going
it is
off.
Better.
Can you? Okay. So, am I audible now?
Yes.
Okay. So, if we put an detector somewhere here, so we will get a neutrino passing through all layers if it's coming from the other side of the Earth. So this is the density profile of our Earth. So, and this density profile is, so this is the radius in kilometers. So starting from 0 to this one, and matter density in gram per cc. So this is the core, and as soon as this is the outer layers and so on. So if something passes through the core, it will encounter the maximum matter density. So that will affect the passage of neutrinos. So this is so when neutrinos pass through our Earth, we can have a coherent forward scattering, and this will introduce a potential, VCC, and for charge current potential and neutral current potential. For our purpose, so this VCC is the one. This is there for all type of neutrinos, but this is only for NUI, and this will be the excess kind of thing which will determine our matter oscillations. So then, so hello, okay. Some other noise is coming. So
I'll check.
Okay. Hello, somebody's mic is not on mute.
Please mute your mic. So
I did. Please go ahead. Yeah.
Okay. Yeah. So now, what is this theta 13? What does this theta 13 have to do with this? So this is the expression of theta 13 in matter, and this we can see that it is related to our matter potential. So the matter potential is a function of our density, and depending on the density, it will also vary. And when this resonance happens, this term cos theta 23 cos 2 theta 13 will be equal to this ACC by delta m squared 32, and this term will become one, that is called resonance. So this resonance, for that we have to have, if this had been 0, this would never have happened. So theta 13 non-zero will help us in probing this matter resonance. So this, I'm just showing how the time evolution will get modified in matter, and this is our of neutrinos. And then we have POS is the oscillation probability of neutrinos, and POS bar is the oscillation probability of antineutrinos. So they will get modified differently according to the sign of delta m squared 31. So this resonance will occur for neutrinos if the true hierarchy is normal, and the resonance will happen for antineutrinos if the true hierarchy is inverted. So what we have to know is, so what is oscillation probability getting modified means that the number of events in our detector will get modified. So if the hierarchy is normal, we'll get a certain number of neutrino events and a certain number of anti-neutrino events after resonance. If the hierarchy is inverted, we'll get a certain number of anti-neutrino events and neutrino events depending on the, this thing. So now detection, so we have to have a detector which is capable of probing the resonance region to determine mass hierarchy. So the main aim of many of the atmospheric neutrino experiments, including INO-ICAL, is to probe the mass hierarchy by probing this resonance region. So if we can identify, if we can probe that resonance region, then we can probe the mass hierarchy. If we can identify new neutrino and anti-neutrino events, even better. Like we can confirmly say that yes, resonance is happening. So that's why ICAL is a very important experiment, because we can magnetize ICAL detector and can separately see neutrinos and anti-neutrino events when we look at mu mu and mu bar. So this is to show sorry, hierarchy, delta Cp, ambiguity. So hierarchy and delta Cp are two unknown quantities right now. And then there is ambiguity, because there is a degeneracy between hierarchy, delta Cp and theta 23. Suppose if we know theta 23, then there will be still hierarchy delta Cp ambiguity. So that means we cannot measure delta Cp irrespective. So hierarchy says this ambiguity means that if we measure delta Cp, both things cannot be measured irrespective of each other. So are there regions where we can actually do this? But that's a very sad thing, right? I mean, we will not know whether this was coming from this combination of hierarchy and delta Cp or that combination of hierarchy and delta Cp. So we have to know at least one of them. Or we have to be able to be in some region where we can measure them irrespective of each other. So if we look at two different baselines, so I'm just showing two different baselines, P mu mu baselines 1300, which is Dune baseline, and 9700 kilometers, which is one of the baselines which we use for atmospheric neutrinos. So here P mu mu is the same for all combinations of hierarchy and delta Cp. So in Dune experiment, if we look at P mu mu probability, that is the disappearance channel, we will not see anything, any hierarchy delta Cp information there. But suppose we look at a very long baseline, that is 9700 kilometer, then we can see that here this is the delta Cp band. So this is the neutrino. This is for neutrino probability. One second. So this is the neutrino probability, and the green things. So this is all. Okay, this is the neutrino probability. This is the neutrino probability, and this is the anti. Sorry, not neutrino. Not anti-neutrino. So this is for NH and IH. So if you look at
Lakshmi, can I interrupt?
Am I getting cut off again?
No. Can I interrupt? You can actually break the full screen, and if you want, you can kind of expand the graphs if you are finding it difficult to look at.
Okay, sir. Okay.
You can come to normal PDF and then expand the graphs.
Oh, like this. Okay. Okay, I'll expand this again because I.
Yeah.
Okay,
okay.
So this is the neutrino. Okay, so neutrino probability with the NH for NH and IH. So for neutrinos, if the hierarchy is normal, resonance occurs, and if the hierarchy was inverted, the resonance would have occurred in anti-neutrino. So that is what these two plots are showing. Now this is for three different delta Cp values. So now we can see that. So this is NH and IH bands. So here the NH and IH bands are different. So that means that we can measure hierarchy here irrespective of delta Cp in such regions. That's why all the atmospheric neutrino experiments are in a good position to measure hierarchy. But now coming to P mu, so this is mu and E mu. So E mu is what for atmospheric. So this is the atmospheric baseline, and this is the Dune baseline. So here, if we look, the effect is in the appearance probability. So appearance probability. So here we can see that the NH and IH bands are just separated for Dune experiment. So Dune experiment, if it looks at the mu to nu appearance channel, it can actually determine hierarchy, and it is very sensitive to delta Cp. So that's why dune, whenever we hear about things about dune, so we are hearing about hierarchy and delta Cp together. So these two bands are separate, so we can measure this is the hierarchy and this is the effect of delta Cp. And in atmospheric neutrino experiments, how can we measure? Now the question is, so this is a different, so that's why we need different experiments and different baselines or different configurations, so as to enable us to determine. So now the question is that can we measure now delta Cp using atmospheric neutrino experiments? So if we look at low energy atmospheric neutrinos, and it would have been nice if we did not have to worry about hierarchy at all, right? So if we look at low energy atmospheric neutrino experiments, then we can actually measure delta Cp irrespective of hierarchy. So at very low energies, what happens that oscillation probability becomes independent of delta m squared 3 2, which is the unknown hierarchy, and hence if we have a very sensitive detector in that energy region, we can measure the delta Cp irrespective of hierarchy in that region. But currently there are no experiments, so this is something which we proposed. Indu Ma'am, Murthy sir and I had a paper, and Dune also has one paper based on that, because Dune is a very sensitive detector, and there is one more paper, analytic paper, which discussed about it. So there are proposals like we can do it, can we do it? So currently there are no running experiment to do this. So now, but like what physics we want to study, and before we go into this thing, I want to mention something called mu tau appearance also. This is all mu appearance experiments. So there were experiments which actually looked at mu tau appearance. If you all remember opera experiment, I will show the picture. So opera experiment became famous for something which it was not designed for. So opera was actually designed to look for mu tau appearance in a very high energy mu beam. It actually found about 10 events and confirmed that mu to mu tau oscillations actually happen. And many of the high energy experiments which are sensitive to high energies, GeV neutrinos, can actually see tau neutrino events also, indirectly if not directly. So now what are the criteria one should look for, like on what basis are we going to make all these GeV neutrino detectors? So first thing will be our energy range. So that energy range energy range and the distance L and E and L, and that will be determined by the physics, which is the L by E. So we have to choose an appropriate energy range and an appropriate baseline, or a combination of all these things. So then what physics do we want to study? Like, do we want to determine hierarchy? For example, ICAL cannot study delta Cp, but we can probe hierarchy. So then the thing is, what physics are we interested in? I mean, are we interested in studying everything together, or are we interested in studying this one particular thing or two particular things? And what other physics we can study? So then so this is the oscillation channel to look at. So what oscillation channel should we look at? For example, all these conventional beams have mu going to something. So mu going to something, mu going to mu means that that's the disappearance channel, and mu going to e was the new appearance channel. And if you could detect nu tau, then that is the mu to nu tau. So in atmospheric neutrinos, if we had a detector sensitive to all three flavors, we will see all of these, all flavors and many wire energies. We will see all these things. So now, so for mu tau appearance, we should have the threshold energy is 3.5 GeV. So only high energy experiments will see that. Now again, so can we detect? So now the question is like, can we detect mu from e or e from mu tau and so on? Can we separate all the three flavors? And along with that, can we separate mu and mu bar, neutrinos and antineutrinos? So we have to make detectors which are sensitive to these things. So so if we want to have a nu detector, we have to be able to separate between a charge current, nu interactions, and neutral current interactions which have pi zero, because they both have electrons in the final state and the showers in the final state, and we will not be if we are not a gamma in the final state, and if we cannot identify these things, then how will we say that it came from NUI or NUICC, or it came from neutral current? So we have to have that kind of ability. And muons are, by virtue of their minimum ionizing particle character, can be detected by many detectors. But again, even if we are considering muons only, if we say, for example, for hierarchy, can we separate mu from mu bar? So we should be able to distinguish these things. So our detector design will also involve all these things. So then detection process. So this detection process, this is what I just said. And how big should I make this detector? So for example, should I make a kilometer cube detector to detect my GeV neutrinos, or can I do with a meter cube detector, or should I make a kiloton detector, or should I make a megaton detector? That depends on the precision with which we want to study things, and the physics again we want to study things. And after all said and done, we have to ask, are we rich enough to make this detector, or like, do we have enough money to make a very expensive detector which can do all these things, or can we do with our whatever resources are available to us and make a not so costly, expensive detector, but we can do very reasonable and good physics with it. So, that depends. That is called cost effectiveness. So we have to take into account all these things. Two more things which I have not put in this slide are, one is the energy resolution of the detector and the systematic uncertainty. So if we have to, whatever detectors we make, if we do not have a very good energy resolution with that detector, we cannot study that physics or L by E properly, and it has to have and several other factors, like we should know the fluxes properly, we should know the cross section properly. So the systematic uncertainties should also be smaller. So now I'll show some pictures of some GeV neutrino detectors. So this is the so T2K I have already explained. So, but I'm showing a Super K detector again because it's a very beautiful detector. So, and here is the beam line again, and this is the ND280 detector, and this is the in-grid detector. So this is off axis and this is on axis, and this is of course our far detector, and these are the events. So if you look at, so I'll just try to enlarge this picture. Can I zoom this? I think this is the maximum. Okay, so there is an 800. So if we look at this, so this is the signal we are looking for. So this is the new-like events, and this is the new-like events. So if you look at so this is a Cherenkov detector, water Cherenkov detector. So the signal will be, if it's a new-like event, this ring will be a sharp ring. But if it's will be a fuzzy ring. So depending on we can apply several event selection cuts and select the events, and these are looking for one ring events in the analysis. And these are the results of. So this is the result from the D2K Nature paper, and there is a slight hint. Okay, one second. There is a slight hint towards maximal CP violation. So this is another detector, which is the NOVA detector. So this is at a baseline of 810. So this is at 295 kilometer, and peak is at 0.6 GeV, and this is 810 kilometer and about 1.4 GeV. And this is the paper from which I have shown this result. So it has taken, this detector is also running. Now this also has a near detector and far detector. So all this, so this detector is like some 14 kiloton big, and these are the dimensions. So I'll again show this. So here, this is made of PVC. So if you see this, so these are extruded, highly reflective PVC structures, and this is filled with liquid scintillator, and there will be highly active liquid scintillator, low Z high tracking liquid, and wavelength shift fiber will be inserted into it so that it will collect the light. So if you see this, this is oriented in one direction. So this is in one direction and this is in the other direction. So that we will get the pixels. So the pixels will be of roughly 4 centimeter into 6 centimeter size, I think. So this is also very big detector, and it is currently taking data. And the near detector is also similar. And here is the event display for this detector. So if we look at this one, so it is like this is the top view and this is the side view. What does that mean? So this, if we look at the detector from here, it's like opening up your book. So this is the top view and this is the side view shown like this. So, and uh, this is a mu like event and this is a mu e like event. So there are clearly distinct characters. So this is like 40 meter, which means that the muon track is very long. So muon is always easily identifiable. And this is electron track, and we know which direction the beam is coming from. So the next detector is, so this is the result. So this is the fit to that their data, and they are all these detectors. You will always find this kind of contour between sine squared theta 2 3 and delta m squared 3 2 from different experiments. So sorry. Okay. So let's go to the next detector. So this is a very important detector. So if you all remember, Opera made a news in 2011. I mean, 2011 that the neutrinos are faster than light, but that was a technical error. It was proved later. But I mean, that was actually not what this detector was made for. This detector was actually made for nu tau appearance detection. So this contains lead and emulsion plate. So this nu tau is very difficult to detect. So nu tau. So what happens is, you have a CNGS beam from CNGS. So this average energy is around 17 GeV, and the baseline is 730 kilometer. So so this, if you remember, Minos experiment also had 730 kilometer, but its average energy was around 3 GeV or something. So it could not see the tau. So then, even though the baselines were different, same energies were different. So here, for Opera experiment, the CNGS beam comes from this direction, from CERN, and then we have something called bricks. So again, I'll do this. So this brick contains lead and emulsion. So why is this emulsion used? Because this length is very small, of the order of micrometers, and this tau will very readily decay also. So we have to have a very fine-grained detector to see this decays, to confirm that yes, it's actually tau which is decaying. So so here nu tau will interact and will produce, this is the charge current interaction of nu tau, and will produce a tau, and this tau will decay into further nu tau and hadrons or leptons, and there will be always hadrons. So 64% of the time, 66% of the time, tau will decay in hadronic mode, and 17% and 17% of the time it will decay to electrons and muons along with other hadrons. So you will have one set of hadrons from the nu tau charge current interaction, and you will have in hadronic interaction, then you will have an extra set of hadrons whose energy you can measure. And then you can look at the event topology when looking at the emulsion. So then you can see that, okay, these kinds of events are happening, and this is called the kink. So it suddenly decays. So this goes there, and this, they are looking for this kink in the detector. But Opera detector also has some electronic components. Why? Because this cannot, lead and emulsion plates are not charged, right? I mean, they are not connected to any live event. It's like taking photo using our old camera. That does not have a stamp of your timestamp on it. But if you do it digitally, you will get a timestamp. So you have to have some digital component. So then it has an electronic component, and this electronic component component which will trigger that okay, this event has come, some will look for that area and will find out. So this brick is packed in some this thing, and instead of opening the entire brick, it has some outside changeable sheet. So first it will look if there is some heat in that changeable sheet. If there is no heat in the changeable sheet, they will not open the brick, otherwise it will be a waste of all the brick and emulsion. So this is a very fine detector, and this has confirmed that nu to nu tau appearance is actually happening. So that was the importance of this experiment. And they also did some fit to delta m squared 3.2. So they found some 2.7 into 10 raised to minus 3. And they also measured the cross section of nu tau and nucleon interaction. So this is one of the very important old generation accelerator neutrino experiments. So now there is Dune experiment. So Dune experiment, many of you will be familiar with. So Dune is also a long baseline experiment, and here the beam energy is around some 3 GeV, and baseline is L 1300 kilometer. So this is a liquid argon detector. So again in this detector, so it will look for new appearance, and this is very important. So that having liquid argon is really important. So here in liquid argon, what happens is, this is a liquid argon TPC. It's a time projection chamber. It will interact with these liquid argon this thing, and will produce charge. So there is a cathode and there are anode planes. So this if we apply a high voltage, depending on the charge of the particle, it will drift so towards the cathode and anode. And there are 3 anode planes. 2 of them are called induction planes, and this is the collection plane. And there is a scintillator. So liquid argon is also a scintillator, and there are some PMTs here. So that PMT will give the drift time. So that time is also used to determine the vertex of this interaction. So this is a very, and the size of this, the pixel size is like millimeter. So here if we look at the event display, we can actually see that so this is a real neutrino track, so neutrino event, and this is a muon which is passing through, and this is again the CNGS beam. So this picture is from the Icarus event, and just to show that what is happening. So the advantage of this is that we can actually see all the individual tracks. So because the detector is so fine grained, so because of that we can actually see if there is a pi 0. So if the pi 0 is there, we'll get 2 gamma, and if it's an electron, then we'll get 1 gamma, and we can measure the d by dx. So if it's d by dx is twice that of 1 gamma, for electrons it will be d by dx, and for pi 0 going to 2 gamma, it will be 2d by dx. So then we can use the topology as well as the energy to determine what kind of interaction it was. So that is the importance of this new CC to pi 0 separation. So we can reconstruct the mass of pi 0 also in this detector. So this is the Icarus detector based on which this technology is being developed. So this is a picture of the proto-Dune detector in CERN. So now let's talk about ICAL detector. So this all of us are, most of us are familiar about ICAL detector. So I'll just show the components. So what all can ICAL do? So ICAL is obviously a magnetized detector, which is this is 48 meter by 16 meter by 14.45 meter, and it has 3 modules. And the central region, again the central region here, this is the magnetized region where the magnetic field is uniform and constant, and it has peripheral region where the magnetic field is uniform but lesser, but here it's lesser than the central region, and it's slightly different, and the side regions are there where it's varying. So this is like the fiducial volume of the detector. And ICAL detector will have RPCs, which are the active detectors. So iron is the one with which the neutrinos interact, and because of so the RPC, how RPCs will detect, Satya sir will give a talk on Wednesday, and here so iron is the target material and RPCs are the active detectors. So this detector is basically a muon machine optimized for muon detection. Why is the muon? Because you need to that resonance region, we can probe that easily with the muon probability. And also atmospheric neutrinos, mu to nu e ratio is twice, right? So we'll have more, muon events. Mu events, a contribution from mu will be more for atmospheric neutrino events. So this is one event display. So this is not a real event display. So we simulated it. So we have a track and a hadron shower. So one difference from is that in iCal, the iron is like 5.6 centimeter thick. So that means you cannot see individual hadron showers like this. I mean, here, this is the actual hadron part of, so this is the muon part and this is the hadron part. In iCal, you cannot see individual tracks like this. You will see a shower, but that is even that, when taken into account into our physics analysis, can give us a very good sensitivity to mass hierarchy. And muon is obviously muon, and we can make use of magnetic field and tell whether it's plus muon or minus muon, and whether it was neutrino or anti-neutrino. And here is the predicted sensitivity to this solely normal hierarchy. And this is an old plot. So this was the T2K and so this was the T2K and Minos results at those time. And this was the iCal analysis. And so this is the magnetic field map, simulated magnetic field map. So if you go to TIFR 217, you will see a 1 by 1 meter stack. So it has about 12 layers, which is detecting live cosmic muons. And this is the prototype in Madurai. If you go to iChep, you will see mini iCal, which has magnet. So this blue are the iron plates and the RPCs. One thing I want to mention is that even for super K, all the atmospheric neutrino experiments. So now that this is a high energy detector, right? So I said about nu tau detection. So nu tau detection means that in iCal also we'll be able to see it indirectly by means of neutral current events. So in this region, we'll be able to separate nu tau events. I mean, this is about the neutral current background. So iCal can detect something called rock muons also. So in all our neutrino detectors, we say that our neutrino is interacting inside the detector volume. So what if the neutrino interacts outside the detector volume and the product muon comes to our detector? We can still detect that muon, and that neutrino would actually have passed through the earth and it has some oscillation information. So by analyzing that upward muon, we call it upward muon, we can still get some sensitivity to oscillation parameter. I mean, it's not as sensitive as our full neutrino interaction inside the detector, but we are neutrino people, so we need to we are low counting experiments, so any extra events are useful. So this analysis was actually done by super K also. They also have enough new samples, so all atmospheric neutrino experiments can do this. So now I will talk about another atmospheric neutrino experiment, which is so this is iron, this was iron detector, right? Now we can have instead of iron, we can have a water detector also. So there are two similar detectors. One is Orca and Pingu, similar in the sense that they are both Cherenkov detectors and put in natural environment. But Orca is put in the Mediterranean Sea, and Pingu will be put in the in ice cube. So it's part of ice cube. It's in the middle of ice cube. So that upgrade is going on. So I will show Orca pictures. So this is a nice depiction of how the Orca strings will have. So Orca will have so many strings, and this is the size of the detector. So I'll show this. Why is it not moving? Okay, 1 second. So this is what the detector will look from above. So it has some densely packed strings. So KM3net has actually another detector called ARCA. So ARCA will have a bigger volume, but that will be for very high energy neutrinos. So this is for the atmospheric neutrino energy. So ARCA is near Italy and ORCA is near France. So they are in the two different locations. So this is the spacing. So they have something called digital optical modules. So these are digital optical modules, and they will look for Cherenkov. This is again a water Cherenkov detector, but the difference between Super K and this is that Super K water is extra pure because we can purify the water. So this is actually sea water. We cannot do anything. I mean, we cannot that it's the actual sea, so we cannot do anything about that. So this has um, it's in the natural environment. So this one digital optical module has about 31 3-inch PMTs, so enclosed in the, and when some particle passes through this, so all these along the path will light up. So this is a simulation of that event. So if so we will get so the strings are hanging, so we'll get several lighted up depending on whether it's a track or a shower. So Orca right now it has so this experiment will also look for mass hierarchy, but it does not have charge ID, but it still can look I mean determine mass hierarchy, because whether we look at depending on the hierarchy, the event spectrum will be there. So we can look at the event spectra and determine the hierarchy. And it's a very massive detector also. So 6 strings have been installed, and I think in January they detected this year. So there were 5 neutrino candidates, and so these are the for those 6 strings. So this is time versus its height of the detector. So its height of the detector is increasing, so we know that it's upgoing, and it's increasing in time. So the slope of this track is plus. So that means it's plus in time. So it's up. It came from up, and this is one so taking data right now. And there is Super K. Obviously, Super K has made a lot of appearances in this PPT, but Super K has been running forever, and then it has done a lot of physics starting from the discovery of atmospheric neutrino oscillation. So it's natural that it will make reappearances. So this is the Super K and Hyper K. So this is the actual Super K detector. So as I said, it's a 50 kiloton detector, water detector, water Cherenkov. Now this is the inside of Super K, and Super K also has. So these are the results from Super K analysis. So it has been. So this is the result from phase 1 to 4, and again this is okay, I'll show. Okay, so this is the delta m squared fit they have done, and theta 23 fit, and also delta CP fit, and there is a mild preference towards normal hierarchy, and this is the fit comparison of the fit with several different experiments. And Super K has 2 samples. One is the sub GeV sample and the multi GeV sample. Energies above 1.33 GeV are called multi GeV. So we have Hyper K now. So now the aim of Hyper K will be, this will be a megaton detector compared to Super K. We can see how small Super K is and how big Hyper K will be. So also Hyper K will have PMTs with much better efficiencies, and the size, it will also look for delta CP using beam, and then this is, and it also can determine mass hierarchy by looking at new appearance. You remember, if you look at so if normal hierarchy is the true one, then the new events will be enhanced, and the inverted hierarchy is this one, though. So this will be the spectra. So it will look for that also. And these are the proposed detectors. So please note that all these detectors can see other sources of neutrinos also. They can look at solar neutrinos, and some of them Hyper K, this Dune, etc. are also, planning to look at supernova neutrinos. So for one thing about Super K detector is that Super K will be doped with gadolinium to make its neutron capture efficiency better, so that anti-neutrino detection will become better. So all these detectors will go, the existing detectors will go to some upgrade, and many other detectors are also coming up. So this is only the standard physics which which we want to study. And then there will be new tau. So if we, so this Orca and Pingu experiments, they will be, they can also see new tau new tau events. So because their sensitivity is in those higher energies. So, and then there is obviously this question of mass hierarchy and delta Cp, and what are the future prospects? Like I said, so low energy sub-GeV atmospheric neutrinos, and then can we make a new detector? What can be used, or can we use existing detector data to look at those things? So again, use how to improve the neutrino versus anti-neutrino detection in existing detectors. Make new detectors with better resolutions and smaller systematic uncertainties. What are the new detection techniques we can use? These are all future prospects, so we can all work on that. So that's all. So thank you. So I'll update the PPT with all the references later. So okay, done.
Okay, Lakshmi, thank you very much for your quite, I think I would say, exhaustive lecture, starting, with a recap of the current scenario in terms of the oscillation parameters, but also went on to describe several new experiments which are already running and also on the verge of commissioning and so on, which I'm sure will improve the numbers very, very drastically. And it's also nice that coming from you, described quite a few future prospects of many gigantic detectors, and including, of course, the I know project as such. I hope there are some questions from the participants. Please raise your hand if you have a question for today's speaker. Let me also look at on the YouTube. Okay. I don't seem to have any.
I just wanted to make a comment.
Any question? Okay, there is a comment from Indu. Yeah, Indu, please go ahead.
My hand is raised, by the way. You didn't tell me to.
Oh, I'm sorry, I didn't see. Yeah.
It's okay. That's why I just.
Yeah, now I see. Yeah.
Okay. No, it's just that I wanted to comment about this, especially for I don't know how many are here, but what is really surprising to me is that it appears as though delta Cp is going to be determined before the hierarchy, which I think none of us actually anticipated. It's something really interesting for me that people seem to be zeroing in, especially the new T2K data. So since most of these, both the low energy accelerator and the reactor experiments are all at low energies, I think that people have finally realized that at low energies, there is this hierarchy independence, and therefore it appears as though delta Cp will be determined. So that's the remark I wanted to make.
Okay. Are there any other questions? Okay. I don't see any more. Okay. There is one question from Unni. It says how they are designing such detectors.
Meaning, what kind of detector?
Yeah. I mean, it looked like a little generic question, but how they are designing such detectors. Okay, maybe you already mentioned in some way, depending on what particular physics one is talking about. Maybe you can throw some light in terms of what is the target material, or some of them are depending on what parameter you want to measure. Some are atmospheric, some are coming from accelerator, and so on. The question is not very clean. I wish if you are on the why can't you ask question yourself, Unni? You are on Zoom, and I am trying to unmute. Can you come up and ask yourself? No. So, do you want to say a few words, Lakshmi?
I mean, that's all I have to say. So, I mean, neutrino physics will all, somebody, last in some talk, somebody asked, they will all be determined and then what next and some kind of thing. But I don't think that the mysteries will not be over every time because if you remember some long time ago, all these will be discovered and then that's the end of physics. But then obviously physics did not end. So there will always be something or the other we will find out as long as we go on taking data and studying further things.
Okay,
That's all I have to say.
that's quite a. Okay, there is another one which is now on YouTube, which I just see
Okay.
appeared on the YouTube. This is from Nafis Rawaz Khan Chaudhary. It says,
Okay.
okay, in MH, independent delta CP measurement at sub GeV energies, do you fit marginalize over the MH to be totally unambiguous of the ordering?
Uh, I mean, MH will not be in the expression at all. No? So then we will not depend on that's at sub GeV. There will not be any dependence on mass hierarchy. So the oscillation probability itself will become independent. So do we have to marginalize over MH there? No, no. I mean, I
I mean,
don't
you
know.
can, but it won't make any difference, right?
Doesn't make any sense. Okay. So I see. I think there are
Can
no.
I add, since
Yeah, yeah. Please.
Lakshmi didn't
Ah,
want to
yes,
answer
sir.
this question of
Okay.
Uni's, I think that there are two different directions. See, INO ICAL experiment is focusing on muon reconstruction. Okay, so both in the accelerator and atmospheric neutrinos, and in fact even in the reactor neutrinos, it's only electron and muon type neutrinos. So nu tau is very small and very like just a couple of experiments looking at nu tau. So everyone's really focusing on the nu e and nu tau, nu mu. So that means if you have a charge current interaction, you want to see muons or electrons in the final state. And all the accelerator experiments start with muon beams. So really, if you want to look at oscillation nu mu to nu e, you want to look at electrons in the final state. So the detectors are being designed to be more and more sensitive to electrons and to the hadrons which come out at higher energies as part of the deep inelastic scattering experiments. Whereas I think ICAL is going in the detection of muons, and also SK being the kind of detector it is looking at both electrons and muons. Because of the Cherenkov radiation, it can see both. So I think when you design detectors and you talk about designing detectors, the main thing that now you want to look at precision is to be able to discriminate these very well. So for example, you want to separate electron from pi naught gamma kind of event, because you want to separate out coherent scattering events from resonance events from electron charge current events and so on. So if that's the kind of question that Uni was asking, well, this is the kind of answer that I can think of.
Okay. Okay. Oh, this is about the designing
Yeah,
detector.
yeah, 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 yeah,
Ah,
yeah.
okay.
Because I think it's a very interesting question.
Yeah,
I
yeah,
think the
yeah.
experimentalists must ask, what is it we are focusing on?
Yeah, but
ICAL made
okay.
that decision 10 years ago that you
Yes,
want to
yes.
look at nu mu. But really the accelerator experiments are really focusing on the electron detection part, right?
Right. Of course, there was also some proposal for even from ICAL like detector to whether or not we can have future modules made for detection of electron. But anyway, but that's a
Yeah.
different topic altogether. Okay, I think it's now time to thank today's speaker for our excellent talk, and also for all the participants who have participated actively in this lecture. And as we already mentioned, of course, we have two other talks lined up later this week. So please come back. All these talks are at 8 or at 6 p.m. So the next talk we are going to have is about how the neutrino interactions are kind of recorded or detected. And the last talk on Friday for this week is going to be by Professor Kazari Mazumdar, who is going to talk about the LHC physics till now and what is going to happen in future. So with that, let us close today's talk by thanking the speaker once again and all the participants.
Okay.
Thank you very much.
Thank you, sir. Please